Hello, so today we're going to be looking at the palindrome permutation problem. And this is a string problem, like it can be found on page 91 of the book Cracking the Code Interview. So this is the problem right here. It says given a string, write a function to check if it is a permutation of a palindrome. A palindrome is a word or a phrase that is written the same forwards and backwards. An example of this would be the word race car, because if you read it forwards, it's RACECAR. If you read it backwards, it's RACECAR. So it's the same forwards and backwards. Permutation is a rearrangement of letters. So if we had ABC, permutation of that would be BCA, BAC, etc., etc. So it's just a rearrangement of letters. It also says the palindrome does not need to be limited to just dictionary words. So here we have an example. So this input Tact Coa, so Tact space Coa, and the output for this is true because we could have Taco Cat, which is a palindrome. I'm guessing we're ignoring spaces here, but we have TACOCAT and then TACOCAT forwards and backwards as well. Another one is acto guitar, which is ACTO CTA and then ACTO CTA backwards as well. So we basically want to see if given an input, can we rearrange it in a way that it forms a palindrome? And again, it doesn't need to be dictionary words, as these aren't really real words. And I'm going to make an assumption that we are ignoring spaces here as well, because the spaces, if you read these forwards and backwards, they're not in the correct place. So the first thing we can do is we can think about a brute force solution. And there's a pretty obvious brute force solution here. So the first thing we want to do is generate all permutations of, let's say the input is string S. So we want to generate all permutations of S. So like I said, if we had ABC, we'd want to rearrange this to ACB, BCA, BAC, CBA, CAB. Like those will be all the permutations of ABC. Then what we want to do is check if each permutation is identical forwards and backwards. So if we were to do that here, we can see that ABC is not CBA, so that's not correct. ACB is not the same as BCA, so that's not correct. BCA is not the same as ACB, so that's not correct. BAC, CAB, not correct. CBA, ABC, not correct. CAB, BAC is not correct. And then what we want to do is if found, if found same forwards and back. I don't know how to describe this better. Return true. Else return false. So once we check through all the permutations, return false. So again, for example, if we had the string, let's say BAA, and we had a permutation ABA, this would be the same forwards and backwards, so we would return true here. Now, this is a brute force solution, so it's obviously not very good. If we think about the time and space complexity of this, generating all permutations is incredibly costly. And this is something like S factorial, where S factorial is basically S times S minus 1 times S minus 2 all the way up to 1. So generating all permutations is really costly. And then For each of these, we need to check if the permutation is identical forwards and backwards. And for that, we would need to iterate through strings, which would be of length s. So this would be order s right here. And these two steps are just comparisons, so they're constant. The time complexity here is we need to do s factorial permutations, and for each of those, we need to do an order s string comparison. So this would be order s factorial times s, which is really not very good. Again, s is the length of the string. If we think about the space complexity, if we were to generate all the permutations and then check them later, it would be order s factorial multiplied by s, because we would need to store s factorial times s characters to do this. But we could also just generate a permutation, check it straight away. So I would say in this case, the space complexity is constant, order 1. So yeah, this is our brute force solution. Clearly it's not very good, but it is a solution, so we can capture that for now. So in order to optimize this, what we can do is really think about what a palindrome is and whether we need to actually check all permutations. So if I were to pull up some palindromes, we can look for some patterns in these. So let's see. So I'm going to write some of these down. So we have Anna, we have Civic, we have Kayak, Level, Race Car, Mom, Dad, etc. And what we can think about is what properties a palindrome has. So as we can see here, to make a string be forwards and backwards, it's roughly the same on both sides. This AN and NA are similar. This CI here and IC here are quite similar. KA and KA here. LE, LE here. Sometimes there's an extra character in the center. So what we can see is that, and if we look at the fact that these have to be similar, the way that this works is they have an even number of each unique character, or the same number of each unique character. So for example, this one has 2 A's and then 2 N's. Here we have 2 C's, 2 I's, and 1 V. Here we have 2 K's, 2 A's, and 1 Y. Here we have 2 L's, 2 E's, 1 V, etc. And the pattern we can notice is that if we had string S, if S has an even length, like here, Anna has 4 characters. So if S has even length, then for it to be a palindrome, it needs to have even number of each character. S should, oops, we can summarize it a bit more. S has even number of each unique character. So here, for example, we have 2 of each character. And otherwise, so if S has odd length, so for example, if we looked at Kayak and Civic here, we can see that S has even number of each character. Well, not exactly each, but one has odd count. So for example, we can see maybe not odd count, odd frequency. So for example, here we can see that we have two C's, two I's. So these are even, but we have the one V. Here we have two K's and two A's, but we have one Y. And it's important to know that you can only have one character that has an odd number. The other characters need to have an even number. So again, here we have two R's, two A's, two C's, and then we have our one E here. So one of these characters can have an odd number. It doesn't exactly have to be one. It could be three, for example. We could have an E on this side and an E on this side, and it would still be valid. So we can make use of this information actually. So I'm just going to save this as well, because this is important information. So we can make use of this fact, and what we can do is basically we can have a way that we can check these properties in our input string. And an easy way to do this would be sorting. So I'll show you how that would work. So let's say we had this one here, Tact Coa. I'm going to remove the spaces and not care about them because they don't seem to matter anyway. So what we can do is we can do a sort of these characters. So we can alphabetically sort these. So we have A, C, C, O, and then T, T, like this. So this is the alphabeticals. These characters sorted alphabetically. And then what we can do is we can just look through the string and check that for each character, the count is even, or at most one is odd. So for example, if we were to go through this, we can see that we have two A's, we have two C's, so that's fine. We have one O, and remember one odd is permitted because this has a length 2, 3, 4, 5, 6, 7. It has an odd length of 7. So one O and then two T's. So we know that this can be rearranged into a valid palindrome. If we had, for example, the string hello, and we were to sort this, we would have E, we would have H, L, L, O, like this. So we have one here, that's fine, because this has 5 characters. Then we have one H, and this is where we know we have a problem, because we have 2 characters that have an odd count. So we know that this is not going to be a palindrome. So this is going to be an optimization that uses sorting. So the first thing we want to do is sort characters alphabetically. I guess we could use quick sort. And then what we can do is iterate through the sorted string. Checking that each character appears an even number of times. So each character should appear an even number of times if S has odd length, one character can have odd count. So yeah, that's how we do it. And the way we can keep track of this thing here is just a Boolean flag. So once we find an odd character, we set it to true. And then if we find another odd character and we already set this Boolean to true, we know that we've got two odd characters, so that can't be. And so if no odd characters or no more than two or no more than one, sorry. If S has odd length, then return true. Okay, so this is our optimized algorithm, and let's see what improvements we made here. So if we were to think about the sorting bit right here, this has a time complexity of order n log n if we use quicksort, or s log s, where s is the length of the string. Iterate through the sorted string. Even if we sort this, we know that the sorted string is going to have s characters. So this is going to be OS right here. This bit, it doesn't matter because we're going to be returning straight away, so we don't need to keep track of anything. And this, it's just, we're just going to be storing a number, which is the count of each character, and then we'll delete that when we move to the next character. So this is a constant time. So our time complexity here is going to be order s log s plus order s. And this order s can just get cancelled out because it's the smaller of the two. So we have order s log s time complexity. If we look at space complexity now, this quicksort, it typically uses O log s space, but at maximum it can use OS space in the worst case scenario. And then for the sorted string, if we need to store it separately, it would need to be order s. But if we can sort the original string, we don't need to use up any more space. So the space complexity in the very worst case is order s, but typically it'll be order s log s. And if we compare this to our original solution, we can see that we've improved the time complexity significantly because we went from s factorial, which is huge, to s log s, which is still big, but it's nowhere near as big. The space complexity is a little bit worse, although it typically wouldn't be this bad. So yeah, we have an improved optimized solution right here. So this is going to be sorting optimization. Okay, so we can still do better than this because if we think about the best conceivable runtime, if we're looking through a string of length s, we know that we'll have to look at each character at least once to check if it's a palindrome. So because we need to count the frequency of characters. So the best time we can look for is actually order s. And it's actually possible to do that using a different methods. So that's what I'm going to show you. And once again, we're going to be using a hash map. So we're going to be making a space versus time trade-off. And I'll show you how we do this. So if you have the same one again, so if you had TACTCOA like this, what we can do is we can create a table where we map character to count. And what we can do is we can just go through the string once, and we can basically count the characters. So if we have T here, and we have 1 here, we have A, 1, and then C, 1, T again, so this becomes 2, C again, which this becomes 2, O, 1, so that's fine, and then A again, which becomes 2. And then all we have to do is we can just check through this table. So we have 2 here, 2 here, 2 here, and 1 here. And since this is an odd length string, this is permitted because we have even count for each character except one which is odd. So with this method, all we have to do is we only have to be looking through the string once. So this is definitely an improvement. There's no sorting or anything required. This does use a bit of extra space because we have to store a number for each character. But we can actually improve on this further because we don't really need to know the exact count of each character. We just need to know if the count is odd or even. So what we can do instead is we can store we can store true if odd, false if even. So what this means is we only have to use one bit to store a boolean here. So this would become true, true, false, 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 and then true. And we can just check that at most one of these is true if it's odd length. Otherwise, just check if they're all false. And the way we can do that is we can, so for example, when we start out here, we just set this to true because it's going to be odd. Then we come here and see that it's odd and we just flip it to an even because we're adding another character. Then we flip it back to odd again and so on and so on. So this is the way we can do this. So I'm just going to write out the rough code here. So I'm going to ignore the method signatures because there's just not enough space. So the first thing we're going to do is we're going to create a hash map, and it's going to map from character to Boolean. I'm just going to call this CM. Then what we're going to do is we're going to go through each character. Whoops. We're going to go through each character in the string. So we're going to go through each character in the string, and the string is just S, by the way. And what we want to do is we want to first check if it already exists. So if cm.has and if we have an entry for C and that entry, so if we do cm.get C, so for the entry for that character, if that is equal to a false, so if what this means is if the entry already exists and it's false, which means it's currently even, then what we want to do is we want to set this to, it should be odd here. I'll explain this again later. Okay, so now I'm going to explain it. So what we're doing is we're firstly checking if there's an entry, and if that entry, this shouldn't be odd, this should be true, since we're storing true for odd. So if there's already an entry and it's odd, then set it to false, so set it to even. Otherwise, just create an entry or replace an existing entry and set that to true. So if we were to look through here, the first time this T, it doesn't have an entry, so we set it to true, so it's going to be odd. The second time we come through it, we get to the T and it has an entry and it's true already, it's already odd, so we set it to even. So we basically fill this out for each character, and by the end we know if each character has an odd or even count. The next thing we want to do is we want to have a Boolean to keep track of whether we already found an odd. We can set this to false to start off with, and then we want to look through this this hash map right here. So we're gonna say for key value of CM, which is our character map, and we want to check if we find an odd count here, so if value is equal to odd, this is where we need to be we need to do some checking. So firstly, if s dot length, so s dot length is even, so if the string length is even and we found a character with an odd frequency, we know that this is definitely not permitted, so we can return false here. Also, if we already found an odd character before, we also need to return false here. So, or odd found true. So if s is an even length string or s is an odd length string, but we already found a character with an odd frequency, we need to return false because we know that it wouldn't be a valid palindrome. Otherwise, what we want to do is just set this odd found to be true. So again, what we're doing here is we go through this map, we get to this O here. S dot length isn't even, so that's fine. And we haven't found an odd yet, so we just set this odd found to be true. If there was another character here, we'd see that the odd found is already true, so we can return false. And again, we return false if the length of this string s is even. So then what we're doing here is once we've done that, and we look through this whole map, we haven't found we haven't found more than one odd character, or we haven't found any odd characters, we can just return true because we know that we have an even count of each character and it would be a valid palindrome. So that's the HashMap optimization right there. Now let's just have a look at the time and space complexity of this. So initializing a HashMap with no entries is constant time. Here we're looking through each character in the string. So this is going to be order s, where s is the length of the string. Accessing a value from a hash map is considered constant time, so this is going to be 1. And we're just comparing a boolean, so instead of a string, so this is also going to be order 1. Setting a value in a hash map is order 1 as well. And then to look through this hash map right here, if we think about it, the length of this hash map is basically the same as the number of unique characters in the string s that we have, because we have an entry for each unique character. So at the very most, this hash map can have order s characters where s is the length of the string, if each character happened to be unique. Otherwise, if we know that we have a specific character set, like if we had all letters, for example, all lowercase letters only, we know that this can be a constant size of 26 because there's 26 unique letters. Or if we were to use ASCII, so for ASCII, for example, there's 256 unique characters. So this will be constant. So for a fixed character set, for fixed characters, fixed character set, this is order 1. So it can be order s or order 1, but it doesn't really matter. So if we think about the time complexity, we have order s and then plus, because this happens after, we don't do it for each of these, plus at worst case order s if we don't have a fixed character set. And this becomes order 2s, which is basically order s. So we've achieved the best possible time complexity. Now, if we think about the space complexity here, like I said, this is either fixed, where it would be, so for character set, this is going to be order 1. So if you had a fixed character set, otherwise, this is going to be whatever the number of unique characters are in the string is how many entries we need to have in our hash map. And we're storing a constant value of a boolean in there, so that doesn't matter. So at worst case, this can be order s. So space complexity is order s or order 1, depending on character set. So if it's fixed character set, order 1, even if you think about every possible character, it's still going to be order 1. So this is fixed. This is constant as well. It can be large, but it's still going to be constant. It doesn't matter based on the string. So yeah, we've achieved the optimum space complexity right here as well. So this will definitely be the most the most optimal solution here. One thing I forgot to mention actually is here there's another thing that we need to do. Remember how we were ignoring spaces and stuff? So what we want to do here is as well is if the C is not a normal letter, so if it's like punctuation or something, do nothing, because we don't want to add it to our map. And the reason for that is, for example, in this one right here, we can see that we have one O. The letter O has an odd number of count, and also space also has an odd number of count. So this would actually fail our test. So we want to make sure that we only add valid letters to the map. Okay, so yeah, we have our optimal solution. So let's capture this as well. And so this is to do with a hash map. Okay, so yeah, now that we have an optimal solution, we can code this out. So this method is called a palindrome permutation. It's going to take S, which is a string. This is TypeScript, by the way, and it's going to return a Boolean. So the first thing we want to do is we want to be setting up our hash map. So I'm going to say const cm. And this is going to be a map that maps between, there's no character data type in TypeScript or JavaScript, so we're going to have to use string. I'm just going to map to Boolean. And we just want to make this a new map. Like this. Then what we want to do is we want to look through each of the characters of our input string. So I'm going to say for const character of S. So we're going to go through each character of S. And the first thing we want to do is, because these characters might have different cases, so we might have capital letters, small letters, or whatever, we want to just convert this all to lowercase, just for simplicity. So I'm going to say const C equals character dot to lowercase. And another thing we want to do is we want to make sure that we we don't, like, if it's not a normal letter, we don't want to care about it, so we can just ignore it. And a very cheap way in JavaScript is to check if something is a valid letter is if we convert it to uppercase and we convert it to lowercase. If they match, it means it's not a valid letter, it's some kind of punctuation, because if it's a normal letter, the uppercase and lowercase should be different. Yeah, this only works for English characters, or at least characters that have cases. I think some Asian languages don't, but it's good enough for us, really, especially for ASCII characters. So the way we can do this is we can say if C is equal to character, which is our original character, dot to uppercase, then we just want to have a continue. So this means just do nothing and just go to the next iteration of the for loop. So the next thing we want to do is we want to do this bit right here. So we want to say if cm.has. So if we have an entry for character C and cm.get, so and the value for that is currently odd, then we want to set this to even. So cm.set. And for even, remember, we're using false. So we want to set this to even or false. Otherwise, just create an entry or replace the existing entry and set it to odd. Yep, so again, we'll set even, then odd, etc., etc. So we just kind of flipping it. And then what we want to do is we want to do the next bit where we check through this. So we first want to have our Boolean odd found, and this is going to be a let because we're going to be setting this later. But we're going to be setting it to false to start off with. And then we want to iterate through each of the values in our CM map. So what we can do here is we can say const key value of CM dot entries. So this is just a way to access go through each key and value of the map. And what we want to do is if the value is true, so this means it's set to odd, and then we want to check firstly if the length is even. So if length percentage 2 is equal to 0, or we already have odd, we already found another one that has odd, then what we want to do here is return false. For some reason it's mad at me for doing that. Otherwise what we want to do is we want to set this odd found to true. So again, if we find one that has an odd frequency, if the length of the string is even, we know that that's not allowed. Or if we found another odd frequency character, then we also know that that's not allowed, so return false. Otherwise, we just need to set this flag to indicate that we've already found an odd character. And finally, at the end of this for loop, once we check through the entire map and we're happy, we can return true here. Okay, so let's test this out. So I'm going to just test this out with the input string to start off with. So you just want to do console.log. One thing we can do actually to make this a bit simpler as well is we can just do console.log key value. We can just print the frequency of each character as well. This is not necessary though. So we can say palindrome permutation, and we want to give our input string of Tact Coa. So let's try this now. Hopefully it works. So if we run demo, for some reason it's only setting the first character. Okay, I believe I've realized what's going on here. Yeah, I actually didn't follow my own code properly, so we should only be setting this to true if this is false, because otherwise what we're doing is we're constantly setting it to true. Maybe that could be it. It might not be, but we'll check it again. Yeah. Okay, so it's still not correct. So let me check again. Okay, I finally understood why this wasn't working, and the reason was because the length of this string 1, 2, 3, 4, 5, 6, 7, 8, it included the space, so it had an even length, and it found this odd character right here, and like we did here, it wouldn't be permitted for an even length string. So what we actually need to do is we need to make sure that when we look at the length of the string, we only look at alphabetical characters. So what I've got here is I've just got this regex right here that just removes all characters that aren't in the range A to Z. So we move it to lowercase first. We remove the characters that aren't in the alphabetical range. And yeah, it's just a regex way to do that. So yeah, that's something you need to be careful of as well. For this step, make sure that when you check if the length is odd or even, we remove the non-alphabetical characters. So if we look now, we can see that it's returning true because we have one odd character right here. If we were to try this with the string Anna, we can see that it returns true because we have two characters, A and N, that both have an even number of characters. If we were to try this with race car, I'm going to try with different cases as well. We can see that this returns true because we have RAC, which both have even counts, and then E, which has an odd count. Yeah, so let's try this with some other random words. So let's try ABC here. And we can see that this is false because we have two characters A and B that have an odd number right here. Yeah, so I guess this method is now working. So I'm just going to put the original string back into here. Yeah, so this is our optimized solution, I guess. It uses order S time complexity, which is the best we can have, and order 1 space complexity, which is also the best that we can have. So this is my optimal solution to this problem. If you have any other solutions or find something better, leave a comment and I'd love to discuss it. Thank you.